Hi, Assalamualaikum. Today we are going to learn lesson 39 buffer solutions in chapter 7 Ionic Equilibria. What is buffer solution? Describe it qualitatively and calculate its pH using the Handerson-Hasselbach equation. Buffer solution is a solution which has the ability to maintain its pH when a small amount of strong acid or strong base is added to the solution. Solution that contains a weak acid and its salt, or a weak base and its salt, are what we call buffer solution. There are two types, acidic and basic. Acidic buffer solution can be prepared by mixing a weak acid and its salt. Example 7.14, the acid is acetic acid, our vinegar, and the salt of the weak acid is sodium ethanoate. Reactions that occur in the buffer solution is acetic acid dissociate partially to produce acetate ion and H+, whereas sodium ethanoate will dissociate completely to produce acetate ion, or ethanoate ion is the same name, plus and A+. So the species that is present in the buffer is acetate ion, H+, H2O, and sodium ion. Whenever a small amount of strong acid is added to the buffer solution, the hydrogen ions will be consumed by the acetate ion to form acetic acid. As shown in the equation, you can see acetate ion reacts with hydrogen ion to produce acetic acid. There will be only a small change in pH because it's not much affected. You can see the concentration of acetate ion decreases, and this reaction will produce more acetic acid. What if we add a small amount of strong base? The hydroxide ions will be neutralized by the acid now. It will form acetate ion and water. As the equation shows, acetic acid will react with hydroxide ion to become acetate ion and water. So here we can see the pH will not be much affected as well. The concentration of acetate ion increases now, and the concentration of acetic acid decreases. Let's say we have a beaker. In the beaker is our buffer solution. Listed down there is the two reactions that is involved. And then we insert acid. What will happen is acid will be reacted with acetate ion to become the green item, acetic acid. So we add more acetic acid there. So the pH is maintained. And when we add base, what happens is OH- will react with the acetic acid, and it will produce the purple item there, the acetate ion, and there you go. It's going to increase the concentration of acetate ion, making the pH is maintained. The second type of buffer solution is a basic one. It can be prepared by mixing a weak base and its salt. Example 7.15 shows that we form a basic buffer solution by adding ammonia, the weak base, together with ammonium chloride, the salt of the weak base. Reactions that occur in the buffer solution are ammonia will ionize in water, and it will dissociate it partially to produce ammonium ion and hydroxide ion. Ammonium chloride will dissociate completely to form ammonium ion and chloride ion. So the species that will be present in the buffer are ammonium ion, hydroxide ion, water, and chloride ion. When a small amount of strong acid is added into the buffer, H plus ion will be neutralized by ammonia to form ammonium ion, as shown in the equation. As a result, there will be only a small change in pH because the concentration of ammonia decreases and the concentration of the ammonium ion increases. But when strong base is added to the buffer system, the hydroxide ions will be consumed by the acid NH4 plus to form the base NH3 and water, as shown in the equation. As a result, there will be only a small change in pH, and the concentration of ammonium ion will decrease with concentration of ammonia increases. Now we have another beaker with our basic buffer solution, and we are going to insert in it a little bit of acid. What happened is the acid is going to be consumed by the ammonia and it will form ammonium ion, making the pH is maintained. You can see NH4 plus, the purple item, is added. And if you add base, the hydroxide ion, the OH minus is going to be reacting with ammonium ion and they will form ammonia and water. So you can see there is 2 more green items being added in the beaker. This will maintain the pH. By having the action of buffer solution, we are going to use Handerson-Hasselbach equation to find the pH of the buffer solution. The pH of acidic buffer solution goes for the reaction below. Find the Ka for the first equation, and then you move the concentration of H plus to the front as subject, and you're going to get H plus equals to concentration of acid divided by concentration of salt multiplied by Ka. If we have Ka, we are able to find the pH by taking negative logarithm at both sides of the formula. On the left, we're going to have negative log H plus. On the right, we're going to have negative log Ka multiplied by negative log concentration of acid divided by concentration of salt, and we're going to get pH equals to pKa plus log salt over acid. Let's do example 7.16, question number 1. Calculate the pH of a solution prepared by adding 2 grams of benzoic acid and 2 grams of sodium benzoate in enough water to make 1 liter solution, given the Ka for benzoic acid. I'm giving you the layout first so that you can predict your handwriting so that it fits that page. There is so many things to write. I'm going to explain one by one. Firstly, you need to find the number of mole for benzoic acid and sodium benzoate, given 2 grams of each substance. So you need to find the molar mass. For benzoic acid, 122 grams per mole, and benzoate, sodium, 144 grams per mole. You're going to get 1.64 times 10 to the power of negative 2 and 1.39 times 10 to the power of negative 2 respectively. And then you are given the volume of the system, which is 1 liter. You have to divide the number of mole with the volume to get the concentration, the molarity. So the concentration for benzoic acid is 1.64 times 10 to the power of negative 2 molar. and sodium benzoate is 1.39 times 10 to the power of negative 2 molar. Now, this is the formula we are going to use. The Ka is given to you 6.3 times 10 to the power of negative 5. Just insert it into pKa by adding negative log. And you're going to add it with logarithm of concentration of salt, 1.39 times 10 to the power of negative 2, and concentration of acid, benzoic acid, 1.64 times 10 to the power of negative 2. You're going to get the answer 4.13 as the final answer, pH. Now, we are going deeper into the topic. Question 2. 1 liter buffer solution is prepared by mixing 0.1 mole of acetic acid with 0.1 mole of sodium acetate. So we know here that we need to find the concentration of both substances first. Calculate the pH of the buffer solution. Okay, we can do it as the one we have done in question 1. But then we have the second step. What happened to the pH if we add 0.02 moles of acid and 0.02 moles of sodium hydroxide? Assuming that the volume of the solution does not change, the Ka given is 1.8 times 10 to the power of negative 5 molar. This is the layout of that page 207. If you notice, my handwriting there is getting smaller so that we can fit everything on the same page. Firstly, we find the concentration of acetic acid and sodium acetate. And then we insert the values in the formula. We want to get the pH. So Ka is 1.8 times 10 to the power negative 5. The concentration is 0.1 and 0.1. We get 4.74. Now, what happens to the pH when we add a certain amount of acid? In this case, we add 0.02 moles of HCl. Firstly, we write down the equation. Acetate ion plus hydrogen ion become acid. So the number of mole initially is 0.1. We've calculated, we are actually given the values in the question, 0.1. And then H plus is 0.02. This is given in the question. 0.1 is the concentration of acid, also given in the question. So what happens here is H plus is going to react with acetate ion that exists in the buffer. So acetate ion will be decreased. So you can see 0.1 minus 0.02 because 0.02 of acetate ion has been reacting with H plus to form here the acid. 0.02 acid is added and here becomes 0 H plus and acetate ion decrease now. So the number of mole for the final stage of the reaction is now established. We have got the new concentration of acetate ion and acetic acid now, which is 0.08 molar and 0.12 molar respectively. And then we put it into the formula. pH equals to negative log 1.8 times 10 to the power negative 5 plus log 0.08 divided by 0.12. We got the pH equals to 4.57. It is not that much of a difference from the previous pH we have calculated. Now, what happens when we add 0.02 mole of hydroxide ion? NaOH is a strong base. So again, we insert the balance equation of when the acid is reacting with the hydroxide ion, and we got back the acetate ion together with water. So how much is given here? 0.02. What is the original number of mole for acid? Is 0.1, and for acetate ion is 0.1. So we're going to use all 0.02. At the end is going to be 0 for the OH minus. Therefore, we are using 0.02 from acid, and it will left with 0.08 moles only. And we're going to increase the concentration of acetate ion because we produced it as much as 0.02. So we got 0.12. So we got the concentration of acetate ion 0.12 molar, concentration of acetic acid 0.08 molar. Insert or substitute into the formula, and we got pH 4.92. It's not that much of a difference from the original pH. As long as it's the same pH 4, it is maintained. Question 3. A buffer solution is prepared by dissolving 0.025 mole of sodium acetate in 250 ml aqueous solution of acetic acid 0.1 molar. Calculate the pH of the buffer solution, and then calculate the pH of the buffer solution after the addition of 1 ml of sulfuric acid 0.1 molar, and then calculate the pH of the buffer solution after the addition of 1 ml of sodium hydroxide 0.1 molar. Given the Ka of the acetic acid is 1.74 times 10 to the power of -5 molar. Here is the layout of our page 208. There's so many things to write, so let's go one by one. If you are still clueless on what is going on here, you should focus on calculating the pH of the buffer solution first. The buffer solution consists of the mixing of two solutions, the acetic acid and the sodium acetate. So given the acetic acid is 0.1 molar, and then we calculate the concentration of the sodium acetate because in the question is given 0.025 mole. That one will be diluted or dissolved in 250 ml. So convert it into liters and we get the concentration 0.1 molar. Now, then we have to look at the formula, Handerson-Hasselbach equation. And we are going to insert the Ka, 1.74 times 10 to the power of -5, together with positive log 0.1 over 0.1. So this will make 4.76. The next step is we want to find the pH when we add a certain amount of acid. This time around, we're going to use sulfuric acid. Now, when we're dealing with sulfuric acid, it's a bit tricky because for 1 mole of sulfuric acid, there will be 2 moles of H+. So the first thing that we need to do is find the number of mole for sulfuric acid. 0.1 is the molarity, okay, multiplied by the volume. 1 ml over 1,000 because this is to convert it into liters, and we get 1 times 10 to the power of negative 4 mole. This is for the sulfuric acid molecule. But one molecule has 2 mole of H+, meaning that we are going to add 2 times 10 to the power of negative 4 moles of H+. Let's look at the buffer action now. The reaction is when we insert or add H+, H+ is going to be reacting with acetate ion, and we are going to form the acetic acid. Initially, the number of mole for acetate ion is 0.025 as given in the question, and we have calculated just now. We're going to add 2 times 10 to the power of negative 4 H+. The original number of mole for acetic acid is 0.025 as given in the question. Now, what is the change that is happening here? So the I's table would be negative X, and positive X, respectively, for each substance. So acetate ion is going to react with all the H+ that is supplied by sulfuric acid, and it's going to decrease its concentration, its number of mole, to become 0.0248. Okay, and H+ is going to be 0. The acetic acid is going to be increased by 2 times 10 to the power of negative 4 to become 0.0252. This is all the final number of mole for every substance. The next step is we put the values inside the Handerson-Hasselbach equation. The thing is, the final figure that we have calculated here is the number of mole. It is not yet the concentration. So what is the total volume of the substance that we are calculating? For acetate ion, it is 0.0248 divided by 0.251. 1 ml is the volume of sulfuric acid we add. And for acetic acid, it is 0.0252 divided by 0.251. Remember, 1 ml is the sulfuric acid that we add. So here we have 4.76 minus 6.95 times 10 to the power of negative 3. The new pH for this system of buffer solution is 4.75. The next step is we want to know the pH when we add a certain amount of sodium hydroxide, 0.1 molar, 1 ml only. So 1 ml multiplied by 1 liter over 1,000, we got 1 times 10 to the power of negative 4 moles. The buffer action is that the OH minus added is going to be reacted with the acetic acid to produce acetate ion and water. What is the initial number of mole for every substance? It's 0.025 for acetic acid. 1 times 10 to the power of negative 4 we have calculated here. 0.025 for acetate ion as given in the question. So as usual, the I's table is going to be negative X, and positive X. So the final number of mole for acetic acid when we minus 1 times 10 to the power of negative 4 is 0.0249. And then 0 for OH minus, we have used it all. And the acetate ion is going to be added with 1 times 10 to the power of negative 4 more because the concentration will increase. So the final number of mole would be 0.0251. The next step would be calculating the concentration of acetate ion and acetic acid. So 0.0251 divided by 0.251. 1 here is the 1 ml of sodium hydroxide. And then the acetic acid would be 0.0249 over 0.251. The same thing here. So the total volume is used. We put all of them, substitute in Handerson-Hasselbach equation, negative log 1.74 times 10 to the power of negative 4 plus log 0.0251 over 0.251 divide by 0.0249 over 0.251. The total answer, the final answer, pH is equals to 4.76. It's not very far away. It's very near to the original pH of the buffer system. Now let's do the pH calculation of basic buffer solution. Ammonium chloride will dissociate completely to become ion of ammonium and ion of chloride. And ammonia is going to be ionized in water to dissociate partially to produce ammonium ion and hydroxide ion. So when we calculate the Kb for the reaction, the second equation there, we can see NH4 plus, okay, divide by NH3 multiplied by OH minus. This is the Kb expression, and we want to know the OH minus, right? So we put as a subject, and the Handerson-Hasselbach equation becomes like this. Taking the negative logarithm for both sides of the equation, we're going to get negative log OH minus equals to negative log Kb multiplied by negative log concentration of ammonia divided by concentration of ammonium ion. So we're going to have POH equals to pKb plus log concentration of ammonium ion divided by concentration of ammonia. Let's do example 7.17, question number 1. Calculate the pH of the solution prepared by mixing 500 ml 0.1 molar hydrazinium chloride N2H5Cl with 500 ml 0.2 molar hydrazine N2H4. The Kb given is 1.7 times 10 to the power of negative 7. Please note that down for orange owners. This is the layout of what you have to write in page 210. The first thing that we need to do is find the pH of the buffer solution. So the salt given, we need to find the concentration. Given to us is 500 ml over 1,000 times 0.1 molar. We got 0.05 mole. And we have to divide the number of mole here with the total volume of the salt and of the base, 0.5 plus 0.5. 500 plus 500. It's 1 liter altogether. So the concentration of the N2H5Cl now is 0.05 molar. Next, we find the number of mole of hydrazine. N2H4 is 0.2 molar multiplied by the volume 500 over 1,000 ml. This is 0.1 molar. 0.1 molar divided by the total volume 1 liter. This makes the concentration of hydrazine is 0.1 molar. By using the Handerson-Hasselbach equation, we insert all the values that we have calculated previously. So POH equals to negative log 1.7 times 10 to the power of negative 7 plus log 0.05 over 0.1. We got 6.47. Remember, this is POH, not yet pH. So to get pH, we do 14 minus 6.47. We got 7.53. Question 2. A buffer solution is prepared by mixing 400 ml of 1.5 molar ammonium chloride solution with 600 ml of 0.1 molar ammonia. Calculate the pH of the buffer solution, and then calculate the pH of the buffer solution after the addition of 0.15 molar sodium hydroxide and after the addition of 0.011 molar of H+. Maybe that comes from HCl. Assume that the volume of the solution does not change when HCl and NaOH is added. Kb for ammonia is 1.8 times 10 to the power of negative 5 molar. This is the layout. Please use a very small handwriting for page 211, everybody. Okay, maybe this one I did not emphasize in question 1. The total volume of the buffer system is the combination of base and salt. So 400 ml and 600 ml, we need to add up to become 1 liter. Then we will find the number of mole for each substance. For ammonium chloride, we got 1.5 times 0.4, making 0.6 mole. And for ammonia, we got 0.1, multiply 0.6, we got 0.06 mole. Both of this figure, we divide by 1 liter to get 0.6 molar and 0.06 molar, respectively. And then we use the Handerson-Hasselbach equation for basic buffer solution. POH is now equals to negative log 1.8 times 10 to the power of negative 5 plus log 0.6 over 0.06, making the POH to become 5.74. The pH now, when we subtract from 14, is equals to 8.26. What happens when we add a certain amount of OH minus to the basic buffer solution that we have produced just now? So the buffer action would be ammonium ion plus OH minus become the base ammonia plus water. The initial concentration is 0.6 molar for ammonium ion, 0.15 molar for the OH minus that we are adding, and 0.06 molar for the base, weak base. What is the change? We have to subtract from the amount of OH minus that is supplied, minus 0.15 for ammonium ion, and we are left with 0.45 molar. This is the final concentration. And then we are going to find the concentration of ammonia, which is now have become 0.21 because we add 0.15 to 0.06. We use the concentration directly here because the question states that we assume the volume of the solution does not change when we add an AOH. The next step would be we use the Handerson-Hasselbach equation, substitute all the values, and we got POH equals to 5.08 and the pH is 8.92. The original pH is 8.26. And when we add OH minus, it became 8.92. It's not that far away. So the pH is maintained. Finally, we are adding a certain amount of H+ into the buffer system. that H plus is going to be reacted with the weak base ammonia, and it will become ammonium ion. The initial concentration is 0.06. H plus is 0.011. Ammonium ion is 0.6. And the change would be negative X, positive X. The X would be the concentration of H plus. And we're going to get the final concentration for ammonia. It would be reduced, which is 0.049. And for ammonium ion, is increased. It becomes 0.611 molar. Substitute all the values into the Handerson-Hasselbach equation and you get the POH 5.84, pH 8.16. Notice that the original pH is 8.26. It's not far away. Therefore, the addition of H plus is being taken care of by the buffer system because the pH now is maintained. Please do practice 7.4, question number 1, 2, 3, 4, and 5. And thank you very much for watching. Assalamualaikum warahmatullahi wabarakatuh.